Okay, since we had a request to help go over and solve the problems from this previous exam, this is exam 2 in Chem 6374. The scores were a bit lower than the first exam, which was sort of expected, but there's I think some benefit in going over the problems and making sure that everybody understands how to do them. So I'm going to go through those all here. I've rearranged the questions a little bit to help make the presentation more organized, but it's exactly the same content as you had on the exam. So I encourage you to follow along and see which parts you went a little bit of trouble with in your own exam. Okay, so what we're going to look at first is the molecule pyrene. So the first few questions dealt with this conjugated polycyclic aromatic hydrocarbon, so the typical aromatic compound with 4 fused rings. And most of us did pretty well on this problem, but I'll still go through it. So the first question here asks us to find the characters for the representations for all the pi cells. So we have to recognize that every carbon atom in this molecule has a perpendicular pi orbital available to form a conjugated pi system. So we're going to put every carbon atom there has one. And so if we count that up, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 on the outside. And then we have 11, 12, 13, 14, 15, 16. So 16 total pi orbitals, 1 in each carbon atom. And then again, to find the characters for the representations, we just have to determine for each symmetry operation in the group how many of those orbitals either stay the same, which means they contribute +1 to the character, move to a new position where they contribute 0, or as can sometimes happen with pi orbitals, they may just change their sign, staying in the same location, in which case they contribute -1, and then just total all of those up. So most of us did pretty well on this problem, as I said. And the first thing to recognize is that, again, there's 16 orbitals, so the character for E is going to be 16. That's the total number of orbitals we have, and all of them would be unchanged under identity. For the rotation operations, I did define the coordinate systems for you because in D2H there are 3 mutually perpendicular C2 axes, so you have to define which one is X, which one is Y, and which one is Z to get the same characters and same representations at the end of it. And so what we did for C2Z, again, is a perpendicular rotation. It's going to rotate the whole thing like this. Oh, come on. Rotate the whole thing like that. And so when we rotate the whole thing like that, every single pi orbital moves. There is no pi orbital that's right on the C2 axis in the Z direction. All of them moved into new positions and swap with other pi orbitals in the compound, so you're going to get a character of 0 for C2Z. Now C2Y is a little bit different because our y-axis goes right through the center here of this molecule. And so when we rotate about y, we're going to be flipping it over about that axis. So the orbitals that are off that axis are going to move and contribute 0, but the 4 pi orbitals that are on the axis, 1, 2, 3, 4, they're going to flip over and change their sign. So if you say the positive phase is facing out of the page, when you rotate that about that axis, the positive phase will flip over and face into the page. So we're going to have 4 orbitals changing sign, which means we get a total character of -4 for that operation. For C2X, X goes horizontally in this coordinate system. And again, in the x-axis, there are no pi orbitals along the axis. So when we flip the molecule about that axis, flipping the top over to the bottom, and as it's drawn here, what we get is all 16 pi orbitals moving to a new position. They all do change their signs as well, but if they move to a new position in the molecule, it doesn't matter whether they stay the same sign or change their sign under that operation, they always would contribute 0. So that's another one that has a character of 0. And then similar for identity, we have, or sorry, not identity, inversion. We have our inversion center right at the middle of the molecule here, and there are no pi orbitals on the inversion center, so when we invert, they all invert to the other side of the molecule, about that center point, and they all switch their sign. But again, because they're all moving to the other part of the molecule, maybe we should draw the operations and elements in different colors. So there's our inversion center there in pink. And when we invert about that, all 16 of these pi orbitals move to a new position, and so we get a 0 for that as well. And then for the reflection planes, so XY is going to be the plane of the molecule. It's a flat planar molecule, and we define the XY plane as that plane. So all 16 orbitals are perpendicular to that plane. When we reflect about that, all 16 of them switch their signs. So again, the positive phase, if you define that as facing up out of the page, when you reflect about the XY plane, that same phase would be now pointing downwards out of the page. So you're flipping the sign of all 16 orbitals. So we get a character of minus 16 for that one. And then finally for XZ and YZ. So XZ is going to be a horizontal mirror plane that goes through like this. None of the orbitals change sign under this reflection, but there are no pi orbitals that are on that plane, so they all would reflect to a new position. So example, these two flipping with each other, these two flipping with each other, and so on. So all 16 orbitals move, so we get a character of 0 for that one. And then finally for the YZ plane, similar to what we saw with the y-axis rotation, we have a mirror plane that goes through like this, cuts the molecule in half vertically. So you do have 4 pi orbitals that are right in that plane. The rest of the orbitals are going to reflect about the plane and move, but the 4 that are in that plane are going to stay in the same position, and they're not going to change signs because the plane is in the z direction, in the same direction as the orbitals themselves. And so you're going to have 4 orbitals that are unchanged under that operation and get a character of 4. Okay, so that's the characters you would get for that. I did not ask you to reduce the representation. You would get several different representations, and you get multiple copies of them. Now the next problem here dealt with determining the equations for symmetry adapted linear combinations. So this is a classic projection operator problem. Now the reality is in the pyrene molecule you have, I believe it's 1, 2, 3, at least 4 sets, or maybe 5 sets even, of non-equivalent positions. So if you wanted to really do the full pi orbitals for this compound, it would be quite an undertaking because you'd have to derive 5 different sets of salx, and then you'd have to mix the ones that have the same representation, which again from symmetry alone you can't really determine to what extent they actually mix with each other. Although since these are all carbon atoms, they would probably have fairly equal mixing in most cases. But nonetheless, we're not going to go through the whole thing. We're just doing the symmetry adapted linear combinations for these 4 orbitals here. So phi 1, phi 2, phi 3, and phi 4 represent one set of the non-equivalent positions. So these 4 orbitals would interchange under all the operations of the group. And this again was a problem that most of us didn't do too badly on, but some of us kind of got some of the representations mixed up a little bit. So probably most likely an issue with the first step here. So the first step is going to be, the way that I like to organize this is we apply each operation in the group, each individual operation for this. I had the wrong point group here. This should be D2H. It was correct in the exam, I believe. But anyway, that should be D2H. That's just a typo in this presentation. But we're going to apply all the operations. It should be a lowercase I, so a couple of issues here that I'll fix now. And we're going to apply every operation in the group. Now in D2H, there's only one operation in each class, so it really just is applying each class of operations, or each individual operation is really the same thing for this molecule. So we're going to select one of our basis orbitals. By convention, I always do it on phi 1 just to not confuse myself. And then we're going to apply each operation. So identity operation keeps phi 1 the same, of course. It's the do nothing. When we do C2z, we're going to rotate phi 1 onto phi 3, and it doesn't change signs because we're not flipping the molecule over. We're just rotating it in the plane. So that it's going to rotate onto phi 3. For C2y, that's going to be this horizontal axis, or sorry, vertical axis. I'm getting confused here. C2y is vertical like this. When we flip the molecule over on this axis, phi 1 rotates onto phi 2, but we're also flipping it over, so it actually changes signs as well. So the result of that operation is to invert phi 1 onto the negative of phi 2. For C2x, horizontal axis, we're going to rotate phi 1 onto phi 4, but again, we're flipping the molecule over, so it becomes negative phi 4. For the inversion operation, phi 1 inverts onto phi 3, but again, we're inverting through the plane, so we're going to change the sign as well. Remember, the inversion operation changes the signs of all 3 coordinates. So phi 1 inverts onto phi 3 and changes its sign, so we're going to get a negative phi 3 there. For sigma xy, That's the plane that contains the whole molecule. And when we reflect about that plane, phi 1 is going to change its sign. It's going to stay in the same location, but it's going to, the shaded lobe, if you want to call it the positive lobe, or showing it over here, is going to reflect down to the bottom and change sign. So we get a minus phi 1 for that. Let's probably do it in the same color. For xz, we have a vertical plane that goes in that direction there. That's going to reflect phi 1 onto phi 4, and it's not going to change the sign this time because we're reflecting through a plane that has a z component to it. So we just flip it to that side, but don't flip the molecule over in that operation. So we get positive phi 4 for that, and then for yz, very similar story. This time the vertical direction, this is going to reflect 1 onto 2 without any change in sign. Okay, so that's what we get. And then again, the next step is going to be to get the equations for the selfs. We're going to multiply this result up here by the characters for those 4 representations that we have for the pi orbital, which I gave you the representation. We didn't have to figure out what the representations were. That was supplied on the exam. So we need the character table to do that. And so let's look at the first one here is B2G. So B2G is 1 minus 1, 1 minus 1, 1 minus 1, 1 minus 1. So alternating plus 1 and minus 1 characters. So we multiply those by the characters, we get phi 1 minus 1, phi 3. And then, so 1 minus 1 plus 1, so it's going to be minus phi 2. This times, I'll write the numbers out, make it a little bit clearer. So we have plus 1 character times phi 1, minus 1 character times phi 3, a plus 1 character times minus phi 2, and then we have a minus 1 character times minus phi 4, plus 1 times minus phi 3, and then so it's 1 minus 1, and then we get a minus 1 times minus phi 1, and then we get, so 1 minus 1, 1, phi 4, and then minus 1 times phi 2. So when we take that across, we get 1 plus 1 is 2 phi 1, minus 1 is minus 2 phi 2, minus 1 and minus 1 is minus 2 phi 3, and then 1 and 1 is 2 phi 4. So we get negative coefficients on phi 2 and phi 3 for this. All of them are either plus 2 or minus 2, so we can reduce out the common factor. So let's finish that one off and just do them one at a time. So we get 1 phi 1, we get, as we said, negative 1s for phi 2 and phi 3, and then plus 1 for phi 4. And then the normalization for that would be 1 over 1 plus 1 plus 1 plus 1 is 4, square root of 4 is 2, so we get 1 over 2. Remember, normalization is 1 over the square root of the sum of the coefficients squared. Sum of the squares of the coefficients. All right, so that's going to be how we get the normalization. Most of us did fine on that part. All right, so that's the first one, B2G. Now when we go to B3G, the characters are 1, minus 1, minus 1, 1, 1, minus 1, minus 1, 1. So it's that pattern there. And so for B3G, we get 1 times phi 1, minus 1 times phi 3, minus 1 times minus phi 2, and then 1 times minus phi 4. Again, what we're doing is just taking the characters from that representation and multiplying it by the results from this first line up here. Then we get the same repeating pattern, 1 times minus phi 3, minus 1 times minus phi 1, minus 1 times phi 4, and then we get 1 times phi 2. So in this case, we still have a positive coefficient on phi 1, 1 plus 1, and then we get negative coefficients on 3 and 4. So 2 is positive as well. Minus 1 times minus 1 is 1, and then a 1 there, so that's positive on 2. For all of these pi orbitals, you're going to get, when you do the projection operator like this, you're going to get coefficients of either plus 2 or minus 2. Those normalize out to plus 1 or minus 1. And so in this particular B3G, we're going to get the negative coefficients on 3 and 4 this time. So there's negative and a negative for 3 and 4. So then the equations would be 1, 1, and then minus 1, minus 1, same normalization constant of 1/2. For AU, the characters are 1, 1, 1, 1, and then minus 1, minus 1, minus 1, minus 1. So the first 4 are plus 1, the last 4 are minus 1. So when we multiply those results, we get 1 phi 1 plus 1 phi 3 plus 1 times minus phi 2 plus 1 times minus phi 4, and then we get negative 1s for the last 4. So we're going to get negative 1 times minus phi 3, negative 1 times minus phi 1, negative 1 times phi 4, negative 1 times phi 2. So what we get then is, again, positive coefficient on phi 1, negative coefficient on phi 2, negative 1, positive on phi 3, and then negative on phi 4. So this time the negative 1 coefficients are on 2 and 4, so alternating plus 1 and minus 1 coefficients. So we get 1, minus 1, 1, minus 1, and that's a 1/2. And then for B1U is the last one. So the characters for B1U are 1, 1, minus 1, minus 1, minus 1, minus 1, 1, 1. So 2 plus 1s on the outside, 4 minus 1s in the middle. So when we multiply by that, we get 1 phi 1 plus 1 phi 3. And then we're going to get minus 1 times minus phi 2 plus minus 1 times minus phi 4 plus minus 1 times minus phi 3 plus minus 1 times minus phi 1. And then we get plus 1 times phi 4 plus 1 times phi 2. So in this cell, every coefficient ends up being plus 1. 1, 1 for phi 1, 1 and 1 for phi 2, 1, 1 for phi 3, 1, 1 for phi 4. So for B1U, we get all plus 1. This would be the one where they're all in phase. So we get 1, 1, 1, 1, and same normalization. Okay, so that's going to be the way we get the SALCs for those, just a classic standard projection operator problem. And then the last problem that we dealt with on the Pyrene molecule was going to be to determine the Mulliken symbols for some of the full pi molecular orbitals. So I gave you the frontier orbitals, HOMO -1 up to LUMO +1, gave you the depictions of those, and asked you to find the Mulliken symbol. Now there's two ways we can do this. The first is that if you trust what you did up here, this is going to be phi 1, phi 2. This is going to be, one more down, phi 3 and phi 4 in the way that I normally know up there. So if you trust what you did up there, you could just compare your equations to what the SALC looks like. And so, that requires you to have full faith in your ability to get these equations right. But if we look at this one here, what we see is that we have the same coefficient for phi 1 and phi 2, both blue lobes on those positions. We have opposite for phi 3 and phi 4. So this equation would be phi 1 plus phi 2 minus phi 3 minus phi 4. Opposite phase on phi 3 and phi 4 from phi 1 and phi 2. So that matches up with B3G that we got up here. So again, we could just look at the equations that we got. It's only going to include those 4 orbitals. We also mix in with the other positions to form the full molecular orbital. But for those 4 orbitals, you can get the relative phasing from the picture, match it up to the equation you got. So that comes up with B3G. Now, the other way to do this, which is probably a little bit safer, because if you made a mistake on the previous problem, you wouldn't want to carry it forward to this one. I did try to check that when I was grading, but I don't think anybody actually did it that way. But the safe way to do it is just to apply select symmetry operations to this orbital, figure out if the sign stays the same or changes. So if it stays the same, it has a character of 1 for that operation. If it changes, it has a character of -1. And then from that, you're able to determine the set of characters and match it up to the representations in the character table. Now, in reality, you don't have to apply all 8 operations, as I'll show you. You just need to choose a subset of operations that allows you to distinguish all the molecule symbols from each other. If you did all 8, you would still get there, but you would just take a little bit longer time than you need to. So the first thing we're going to do is the character for identity will always be 1 for all of these, of course, so that's not going to help us. But if we look at the C2z operation, we see that in the character table down here, C2z has a character of +1 for A and B1, and C2z has a character of -1 for B2 and B3. So by applying 2 out of the 3 rotation operations, or 2 out of the 3 reflections, if you prefer that, you can do either rotation. But you don't have to do all 6 of the rotations and reflections. You really just need to do 2 of the 3 of either the rotations or 2 of the 3 for reflections, and that should be enough to distinguish A from B1, from B2, from B3. So let's see how that works. So if we start with C2z in this molecule, when we do the C2z operation, if we start at the top here, this blue lobe is going to rotate down onto a green. So that means we're changing the sign under that operation because blue changes with green. That's indicating the 2 different signs of the pi orbital in that molecule. So because we changed the signs under that operation, that means C2z has a character of -1. And so what that tells us, because we have a character of -1 for C2z, is that it's either a B2 or a B3 representation. And then to distinguish B2 from B3, we actually have to, I misspoke earlier, we do have to apply both of the other, no, we only have to apply one of the 2, C2y or C2x, that will distinguish B2 for B3. So choose whichever one you want to do, it doesn't really matter. I'll do C2y just because it's next on the character table. And so with C2y, when we flip the molecule over that way, we have blue going on to green, green going on to blue as we flip the whole molecule over. So that's going to be a character of -1 for C2y. So what that tells us is if we have -1 for C2z and -1 for C2y, we have to be dealing with a B3 representation, either B3G or B3U. And then to distinguish G from U, we just need to do inversion. So when we do the inversion center, this blue one up top reflects to a blue one on the bottom on the other side, or this green area up here, if we go through the inversion center, inverts onto a green lobe that's below the plane. And so in that case, we're not changing the sign under inversion, so we get a +1 for inversion. And those 3 operations together allow us to distinguish it as B3G, because if it's symmetric with respect to inversion, that makes it B3G. So we could do the other 5 operations. I mean, you get 1 for E, and you could do the other 4 to figure out what those characters are, and they should all match B3G, but that set alone, there's no other representation that has -1 for Z and Y, and +1 for identity. So just those operations can distinguish this as B3G. So we got B3G doing it both ways. So let's go on to the next one and do the same thing. So again, we're going to just do a subset of operations. We'll start with C2Z to distinguish some of the letter parts of the molecule symbol. So in this orbital here, when we do C2Z, green rotates onto blue, blue rotates onto green. So whichever part you focus on, we are changing signs under that operation. So we get, in this case, a -1 for C2Z, same as we got up there. And then when we do -1 for C2Z, and then we're going to do C2Y next, because the ones that have -1 for C2Z are either B2 or B3, and then C2Y can allow us to distinguish those. So C2Y is going to be this one here. And this time when we flip the molecule, this green lobe on the top is going to flip over to a green lobe on the bottom, or this blue one on the top is going to flip over to the blue one that you can kind of see on the bottom. So flipping the molecule about the y-axis preserves the sign or the symmetry of the SALC, and so that is a +1 for C2Y. So the representations that have -1 for C2Z and +1 for C2Y are all B2. And again, we just now have to distinguish if it's G or if it's U by looking at the inversion symmetry. So when we go through the inversion center at the center of this molecule here, green inverts onto a green that's below this one here. This blue inverts to a blue down there. So whichever lobe we choose is going to invert onto a lobe of the same phase or the same color. So we get +1 for identity, telling us that it's now B2G to match that set of characters there. We could have also looked at the equation for the calc. So again, if this is 1, 2, 3, and 4, following what we did in the previous problem, this one's going to be phi 1. We have an opposite phase for phi 2, the same phase for phi 2 and phi 3, so also a negative for that, and then phi 1 and phi 4 are the same. So this one is 1 minus 2 minus 3 plus 4, and that matched up with 1 minus 1 plus 3, which one was that? It's this one here, sorry. Did I screw that up? I'm looking at the wrong one, I'm sorry. 1 minus 2 minus 3 plus 4. So the negative ones are on the middle two, so that should be B2G again. So we did get the same answer both times there. So the equation 1 minus 1 minus 1 plus 1 matches the picture of this orbital, 1 minus 1 minus 1 plus 1, or from the characters we get B2G. So there are two ways to do that one, as I said, and you can get there either way. All right, the third one in this series, we'll go through a little bit more quickly now. So C2z rotates green onto green, or blue onto blue, whichever one you want to focus on. So we get a +1 for C2z, and then for C2y, if we do that one next. So now we have a +1 for C2z, that means it's either A or B1. And when we do the C2y, green rotates onto green, blue flips over and rotates onto the blue on the bottom. So we get +1 for C2y. And so that means, again, +1 characters for Z and Y makes it either AG or AU. Those are the only representations that have +1 characters for both of those first two rotation operations. And then we just have to do inversion to distinguish G from U. So in the inversion operation, this green inverts onto a blue that's at the bottom, or this blue here rotates onto a green that's below the blue. So we change the sign under inversion. This one is asymmetric with respect to inversion, and because of that, that identifies it as AU. So this one is AU. Sorry, I should do it lowercase if we're being precise. And that should match the equation. So this one is going to be 1. We have opposite phase for 2, same phase for 3, opposite phase for 4. And so that one would come out to AU, matching the equation we got above as well. All right, last one here. This one looks to be the in-phase combination of 1, 2, 3, and 4, the subset that we did before, which we came up with B1U for that. And let's see if we get that from the characters as well. So rotation about Z gives us a +1 character, because we're rotating blue onto blue and green onto green. So we get a +1 for C2Z, making it either A or B1. For C2y in this case, though, when we flip the molecule over by that axis, we're going to flip the signs of the orbital. So the 4 that are along the axis flip over, and the green will now point down, or these 4 blue ones, when they flip over to the other side, blue will now point down. So we change the sign under C2y, so we get a +1 and a -1 for Z and Y, indicating that it's a B1, either B1G or B1U. And then for the inversion operation right here at the middle, again, we can either take the central orbital here or the central lobe and inverts to the bottom, green onto blue, or if we take the top one, we go through the inversion center, green inverts onto a blue lobe at the other side. So we get -1 for inversions. This would be a U symmetric orbital, making it B1U. And again, the equation for this is all in phase, 1 plus 2 plus 3 plus 4, because at those 4 positions, all the lobes are blue, all the same phase. Okay, so that's how we would do that one. Again, it's sort of working backwards from the picture of the orbital to the Mulliken symbol, which usually involves finding some subset of characters for the operations, depending on whether the orbital stays the same or changes signs under those operations. In reality, you don't have to do it for all 8 of them, because just this subset of 3 is enough to distinguish all the possibilities that we have. All right, now we're going to move on to this next problem here that dealt with this platinum acetylide molecule. And this one, I think, is the one that most people had the trouble with on the exam. So it's a square planar molecule, but it has two different ligands and trans to each other. So two NHCs that are trans, two acetylides that are trans. So it's going to, it's going to roughly approximate the square planar case, but it's also going to be, a little bit different because we have two different types of ligands. So here, the first question on this molecule dealt with finding the representations for the salix for different subsets of the orbitals here. Now, again, there's a couple ways to do this. We could derive a representation for those orbitals by just applying all the operations and seeing how many of the orbitals move, how many of them stay the same, and then reducing the representation. That's one way to do it, and that's not too bad in this case because there's only a basis set of two orbitals for each case. Or alternatively, because there's only two orbitals, we could just draw out the in-phase and out-of-phase combinations of those two orbitals. If you have two orbitals, your salix are only going to have two possibilities, either in-phase or out-of-phase. And so if you draw those two, you would figure out then the representations for each of those individually. So that's going to be, two ways to do it. We'll do it with the characters first. And so if we start with the NHC sigma salix, which are those ones and those ones there. So for the identity operation, there's two orbitals. When we do C2z, both of them move, so we get a character of 0 for that. C2y, both of those orbitals are in the y direction, so rotation about y doesn't change either of them, so we get a character of 2 there. But then C2x is going to flip the two onto each other, so we get a character of 0. So again, remember, if the orbital stays the same, it contributes +1. If it moves, it contributes 0. If it changes sign, it contributes -1. For sigma orbitals, it's either going to be +1 or 0. For inversion, the two invert onto each other, so they both move. For xy is the plane of the molecule, so both of those orbitals are in the plane, so we get a character of 2 there. And then for xz, that's going to be the horizontal one, that's going to reflect them, it's going to give us a 0. And then for yz, those are in the plane, so we get a character of 2. So when we reduce this representation, again, we could apply the full reduction formula, but you have to do it for all the representations. But we can again see that we have a certain set of non-zero characters here. So we need to look for representations that have characters of +1 for y, xy, and yz. So characters of +1 for y, xy, and yz. So that would be an AG. And the other one that has a character of +1 for y, xy, and xz would be y, xy, xz, so that would be B2U. So because we have non-zero characters for y, xy, and yz, that means the representations that reduces to need to have +1 characters for y, xy, and yz. So that's going to be AG and B2U. All right, so we get AG and B2U for those ones. The other way, again, is you could do it is to draw out the two in-phase and out-of-phase combinations. So if you had, those are going to be the sigma ones there. So the in-phase would look like that. Out-of-phase would look like that. And so this one here has positive orbital density in both the in the y and the -y direction. So this one would transform as y squared. And if we go to the character table, y squared falls under AG. This one has positive density in the y direction, but negative density in the -y. So this one would transform the same as y, or imagine a py orbital would line up with that perfectly. And the representation that includes y is B2U. So there's sort of, again, two ways of doing this. We either come up with a representation and reduce it, or we can draw the two in-phase and out-of-phase combinations and figure out by symmetry matching what they line up with. So this one would be y squared, this one would be y, so we get AG and B2U that way. Next one is the acetylide sigma salix, which is very similar, but just in the x direction. So if we do the characters for those, there's two sigma orbitals, basis orbitals, one on each acetylide there and there. And so we get a character of 2 for C2z that rotates both of them, so we get a character of 0. C2y flips them onto each other, so we get a character of 0. Both of those are in the x direction, so we get a character of 2 for x. Inversion inverts them onto each other, so we get a character of 0. They're in the xy plane, so we get a character of 2. And then xz, they're also in the x direction, so we get a character of 2 for that. And then for yz, that's going to reflect them onto each other, so we get a character of 0. So I'm going through this a little bit quickly, but those are the characters that we get. And so now we just need to find the representations that have +1 for x, xy, and xz. So x, xy, and xz, that's going to be ag. And then x, xy, and xz is b3u. So for this one, when we reduce this representation, we get ag and b3u as the two Mulliken symbols, or again, we can draw the two combinations. In this direction, you'd have the in-phase combination has positive orbital density in both the plus x and the minus x directions. So that's going to be transforming as x squared, which x squared transforms as ag in this point group, totally symmetric. And then the out-of-phase combination would transform as x, because you have positive x in one direction, negative x in the other direction. So this would line up with the x orbital, px orbital, or the x Cartesian coordinate. X transforms as b3u in this point group. So you could also identify it that way, as we said. So I'm going through sort of two ways of getting this. You only really need to do one of the two to get the answer, but however you're most comfortable. So we get ag and b3u for those calcs. Now we're looking at the in-plane acetylide pi star calcs. And so in reality, this is a pi star orbital on each acetylide that forms our basis set. Because the symmetry for pi and pi star orbitals are the same as we talked about when we discussed pi acceptors versus pi donors, if it's easier for us, we can kind of just ignore the other lobe of this orbital. Because whether we consider a basis set that just has a p orbital on each carbon, or a full pi star orbital for the CC triple bond, however we define the basis set, we'll get the same representation. So in reality, we're just looking at a basis set that has these two orbitals here. Now, the only difference with pi orbitals is that in some of the operations, we might get negative characters, as we'll see. So if we do it with the approach of applying the operations and getting the characters, we have two in-plane pi orbitals for the acetylide. Each of these Salk subsets that we're considering just has two basis orbitals. For C2z, it rotates them both onto each other. C2y flips them both onto each other, so we get character of 0. But now for C2x, because these orbitals are along the x direction, when we rotate about that, we're going to flip them over and change the signs. The shaded rotates onto the unshaded and vice versa, so we get a -2 for x. For inversion, they invert onto each other, so we get 0. Both of these are in the xy plane, these in-plane orbitals, so when we reflect about that doesn't change their sign, so we get a +2 for xy. And then for xz, again, we're cutting them in half this way horizontally, so that's going to reflect the two opposite phases onto each other, meaning we're changing the sign for those, getting a -2, and then yz is going to reflect them onto each other, so that gets a 0. So when we reduce this representation for this set of pi orbitals, we need characters of -1 for x and xz, characters of +1 for xy. So let's find the representations that have that. So we need -1 for x and xz, and then +1 for xy. So that should be b1g is one of them, -1 for x, -1 for xz, +1 for xy, so that's b1g. And then we have -1 for x, -1 for xc, +1 for xy. So those are the ones, that's going to be b2u. So we get b1g and b2u when we reduce that representation. This one might be a little bit harder to do with sort of symmetry matching, but again, if we do the in-phase combinations of these, again, just looking at the one lobe of the p orbital, we don't have to consider the opposite side as well, or we do the out-of-phase combinations. So by symmetry matching, this one should symmetry match with the py orbital, and py does transform as b2u, so that's where the b2u comes from. So this combination would be b2u. This one should be symmetry matched with, that's the xy plane, so this should be dxy. it's symmetry matched with that. And if we go to the character table and find xy, that transforms as B1G. So that's where our B1G comes from. So again, symmetry matching works for that as well. Okay, so we get B2U and B1G, however we choose to do that one. All right, now what we're looking at are the out-of-plane acetylide pi star salx. So this is going to be, again, p orbital here and here, or the whole pi star if you want to consider it, but really, again, just one set of p orbitals. The difference between these ones is that the p orbitals are now facing in the z direction, so they're coming out of the page. So when we do the representation for this set of pi orbitals, also on the acetylide, the horizontal ligands there, 2 for identity. For C2z, we again rotate everything onto each other, so we always get character of 0 for that. For C2y, we're going to flip them over, so that's going to get a character of 0. And then for C2x, we flip the whole molecule over in the x direction, so those orbitals stay in the same place but change signs. We get -2 for x. And then what we get for inversion is 0 because they invert onto each other. For the xy plane, which is the plane of the molecule, that's going to reflect this perpendicular p orbital that's facing up and reflect it now facing down with the shaded lobe going down, or again reflecting those two onto each other. So we get -2 for sigma xy. We change the signs of both of those p orbitals under that operation because they're perpendicular to the xy plane. For the xz plane, we get a character of +2 because those orbitals are in that plane. And then for yz, we reflect them onto each other, so we get a character of 0. So to reduce this representation, we need characters of -1 for x and xy, and a character of +1 for xz. So if we find the representations that have that -1 for x and xy, that's going to be B2G, +1 for xz, so that's one of them, is B2G, -1 for x and xy, +1 for xz is B1U. So we get B2G and B1U when we reduce that. I'm not going through all the math on that, but just doing it sort of by inspection. So B2G plus B1U for that. If we try to draw out the in phase and out of phase combinations, a little bit harder because they're perpendicular now. But if we just look at the top lobe only for those, if we get our in phase combination, that's going to have 2 orbitals facing in the z direction. So that's going to transform the same as the z-pz orbital. And so when we find the z coordinate, that's going to be B1U, which is one of the ones that we got. And then if we do the out of phase one, a little bit harder to visualize because it's perpendicular to the page, but our DXZ orbital, because it would have orbital density in the z direction and the x direction, so DXZ would be lined up with that. That would be maybe a little bit easier to draw from the side. So if we draw it from the side, this is x, this is now z. That one is going to be symmetry matched with xz. All right, so this one is symmetry matched with DXZ, and the DXZ orbital, sorry, I have to keep flipping back and forth, is B2G, which is the other one that we got. So I think, again, whichever of these approaches you're more comfortable with should work. Either symmetry matching to basis orbitals or finding representation and reducing it. All right, and then the last one we had were the p orbitals that are on the NHC. So that's going to be these two here and here, also facing in the z direction, but now oriented on the y-axis instead. So if we do the characters for those, either those two or those two there, we get a character of 2 for identity, always 0 for C2z because we're rotating the whole molecule. For C2y, in this case, those orbitals are in the y direction, so when we flip it in that direction, they stay in the same place but change their signs. That's where we get a -2 character. C2x flips them onto each other so they both move. Inversion inverts them onto each other and changes their signs so they both move. For the xy plane, which is perpendicular to those two basis orbitals, so here again we're talking about the NHC p pi salx, that's going to be those ones and those ones. Those are perpendicular to the xy plane, so they reflect and change signs under that operation. For xz, those orbitals are out of that plane, so they move onto each other. We get a character of 0. And then for yz, those orbitals are in the plane, and so they stay the same. We get a character of 2. So to reduce this representation, we need representations that have characters of -1 for y and xy, and +1 for yz. So y and xy are -1, y and xy, and then +1 for, oops. Is it what? Sorry, yeah, yz, my bad. All right, so we need -1 for y, -1 for xy, +1 for xz, so that's b3g, and then -1 for y, -1 for xy, +1 for yz, that's b1u. Okay, so we get b3g and b1u for those orbitals when we reduce the representation. And then if we try to do symmetry matching for that, we would have two perpendicular orbitals facing the z direction. So again, those would transform the same as the z coordinate, which transforms as b1u in this point group. Or if we did the out of phase combination, again, you have to visualize things in 3 dimensions here. That would be the same as our yz orbital, because the yz orbital, which would have lobes in both the positive and negative y direction, would have symmetry matching with this out of phase combination. So if you want to do it from the side, this one's even harder to do because it's in the y direction. But essentially, you'd have this one would be yz, which is going to be our b3g. All right, so that's going to be all the SALCs that we get for those. Again, just in phase and out of phase combinations of the two basis orbitals, or a representation that's fairly simple to reduce because they each have just 3 non-zero characters outside of identity, and you just find the representations that have those same combinations. All right. So the next one here is asking us which of the valence 5D orbitals are the appropriate symmetry to engage in sigma bonding interactions with the ligands. So for this one, there's sort of 2 ways of doing it. Probably the more straightforward way, again, if you did the previous question right, would be to just look at the representations that we got for the sigma orbitals. So we did a set of sigma orbitals on each one. And so for the sigma orbitals, what we got, if we flip back to that, was for the NHCs, we got AG and B2U. And then for these acetylides, we got AG and B3U. So our sigma SALCs are going to have representations of either AG, B2U, or B3U. Those were the sigma SALCs that we got. So if we look at the character table, all the d orbitals are going to have G symmetry. Remember that they're always Garada, always symmetric with respect to inversion. So we don't have to worry about those two. There's no d orbitals that would transform as B2U and B3U. But for the AG representation, we have z squared. Now this one is written in a weird way, but this is going to be dz squared is the obvious one, and then there's also going to be x squared minus y squared. It's not written as that, but it has x squared and y squared separately, and so that's where the x squared minus y squared would also transform. Think about x squared minus y squared, that's going to be this orbital here in the orientation of this compound. And so if you had a sigma SALC that's one phase in the y direction, opposite phase in the x direction, those would both be AG. That'd be a combination of 2 AG SALCs from the 2 different ligands. This is DXY, and so that would also be AG. So under the AG representation, they're not degenerate, they're 2 separate orbitals, but they have the same representation, and so both z squared and x squared minus y squared. Now in reality, we can also remember that, from an octahedral compound, the one that we worked with the most, these are the 2 orbitals that have sigma interactions with the ligands. And for a square planar compound, we're just taking off ligands from the z direction, but we still have all the sigma orbitals in the xy plane that can interact with x squared minus y squared here, or for dz squared, remember, it's going to be the ligands that interact with the torus on the outside. So we have, in a square planar fragment, we also have sigma interactions for both of those. So that's how we get the sigma interactions. The next one asked us, which of the 5D valence orbitals are the appropriate symmetry to engage in pi back bonding with the acetylide ligands? So acetylide ligands are in the x direction, and so we would have, again, in phase and out of phase orbitals there. We actually already talked about this a little bit when we were deriving the representations for these. And so we can have either both of those lobes facing the same or both of them being opposite each other. And again, what we found was that the representations for these, which is helpful to look back at, was B1G and B2U for these are the in-plane ones. So in plane is going to be B2U and B1G. And then for the out of plane, which I'm not going to draw because they're a little bit harder, the out of plane was, which one was the out of plane one up here? Was B2G and B1U. But again, what we have is two ligands in the x direction that have pi orbitals in the y and z directions. And so what that means is that this combination here would interact with dxy, which does transform as B1G. And these out of phase ones, again, all the d orbitals are going to be Garada. That's going to have pi orbital density in the x and z directions, which means it would interact with dxz, which is B2G. So we can look at the representations or we can just do symmetry matching, but either way what we find is for the B1G SALC, that transforms as dxy, the B2G transforms as xz, and so dxy and dxz. And again, that's no different than any regular square planar compound. If you have ligands in the x direction, that's the direction that these two acetylide ligands are in, they're going to have, and they have pi orbitals that are both in and out of plane, so two pi orbitals on each donor atom like we have for the acetylide. Those pi orbitals are of the appropriate symmetry to interact with xy and xz, the two d orbitals that have orbital amplitude in the x direction to be able to interact with both of those sets of pi orbitals. And then finally, we want to know which of the ones are of the appropriate symmetry to engage in pi back bonding with the NHCs. So those are going to be the ones that are in the z direction, and the only difference with the NHCs is that they only have one pi orbital each. So for the NHC ligands, which are, again, these ones here at the top, these are the pi orbitals that we're considering now. Those pi orbitals, there's only one on each ligand, so we don't have both combinations, we just have the one that's perpendicular to the plane or in the z direction. So we have, again, the in phase or out of phase combinations of those two. And as we already found, this one was B1U, and there's not going to be any d orbitals that have Ungarada symmetry, so we can eliminate that one as being possible. But then this one was in the y and z direction, so this was dyz, which transformed as B3G. All right, so we got the B3G representation from that orbital, and that, again, in the character table matches up with dyz, either, again, from the character table or by inspection. So dyz would be the correct answer for this one. That's the orbital that can interact with these two p orbitals. It has density in the y and z directions. These two ligands are in the y-axis and have their p orbitals facing the z direction. So the only difference with the NHC ligands at the top is that they don't have an additional pi orbital in this direction that would be able to interact with, in this case, it would be the XZ, sorry, the XY orbital. So there's no interactions with the XY orbital because there's no pi orbital on those ligands that face that direction. So there's only one set, so it only interacts with DYZ in that case. All right, and then finally we want to know which platinum valence d orbitals are expected to be unoccupied in the ground state. So even though the degeneracies of these are going to be a little bit different, these are going to roughly follow the square planar orbital splitting diagram. So remember, for square planar, we start with octahedral, and then when we remove ligands from the z-axis, we're going to have, if we go to D4H, this one's again D2H, that's even lower symmetry than this. In D4H, it depends on obviously which type of ligands you have, whether they're pi donor or pi acceptor, but in either way, when we descend in symmetry from OH to D4H, we remove ligands along the z-axis, and we would get this is going to be XZ and YZ, and this is going to be DXY. We don't affect the DXY orbital. And then our DZ squared comes down in energy because we're removing ligands from the Z direction, and then our DXY stays the same because it's unaffected by removing ligands. So that's what we got for square planar, which we did in class. And then D2H would be a little bit different than this. We'd have to also relax the degeneracy of XZ and YZ. So these would split in some way when we go to, to D2H. And so the ordering of these bottom three orbitals, these are all of our pi symmetric orbitals. That depends on the type of ligand we have and which direction they're oriented in. So the ordering of those might all be different, but for this problem it doesn't matter. And then we have our DZ squared, which still has sigma interactions along the XY plane, and then our DXY. These are the sigma ones. So that's going to be the orbital splitting diagram, where again the ordering of the bottom three, which are all pi symmetric, can change depending on the types of ligands we have. But in this compound here, we didn't do the d electron counting yet, but this is two neutral ligands, NHCs, and two anionic ligands, which are acetylides. I maybe should have made that more obvious, but it's a square planar platinum compound, and so it should be D8, as is always the case for square planar platinum. So this is a D8 compound, and so when we fill this orbital diagram, whatever order these bottom ones come in, they're all going to be filled. And so the only one that's going to be, sorry, this should be x squared minus y squared. I've effed that up already. My bad. I'm trying to do this too fast. All right, so dx squared minus y squared is going to be the one that's unoccupied. That's the one that has sigma interactions with all four ligands, so it's going to be the most destabilized by virtue of those sigma antibonding interactions. And in a D8 compound, that one would be completely unfilled. So it's our dx squared minus y squared that's going to be unoccupied. And again, this is basically just a square planar molecule. You just have two different ligands in the x direction, two different ligands in y. So that changes the degeneracies of the bottom three orbitals, XZ, YZ, and XY. But the one that's always going to be unoccupied is x squared minus y squared. And then finally, if the NHC ligands are replaced with CO ligands, what would be the effect on the DYZ orbital? So as we determined earlier, the DYZ orbital up here has pi backbonding interactions with those NHC ligands. All right, so the DYZ has pi backbonding interactions with the NHCs. And remember that pi backbonding interactions are stabilizing. So if we have our DYZ orbital and it undergoes a pi backbonding interaction, it's going to be destabilized by that pi interaction. Sorry, it's going to be stabilized by that. And if we introduce a stronger pi acceptor, which is going to make a stronger back bond, that's going to have a stronger bonding interaction, which means it should decrease in energy. So whenever you have pi accepting ligands, these have empty pi orbitals for the metal to back bond into. If you make that a stronger pi acceptor, you're going to stabilize that orbital to a greater extent. And that's going to be true for any time you have pi back bonding involved. So we had to recognize that these were pi acceptor ligands because they have empty p orbitals, and when you replace one with a stronger pi acceptor, you're going to stabilize it to a greater extent. All right, so that question was a bit of a bear. I admit that one was tough, so that was kind of the one that sort of separated people out in terms of their scores. The next question is more straightforward. So this one deals with term symbols. So we have a D5 configuration here. should be superscripted, but it's D5 configuration. And we want to know the sextet and quartet terms. So for D5, we have also some doublet terms, but that would take a while to go through. So I just asked for the two highest spin configurations. So for a sextet, 2s plus 1 equals 6. That means we have all 5 electrons unpaired. So that's going to be D alpha 5, D beta 0. And we just need to get the partial terms for those. So there's sextet terms. For D5, that's going to be an S partial term. And then for D0, that's going to be an S partial term. So the only sextet term we get is sextet S. And then for the quartet terms, that's going to be when we have 3 unpaired electrons. So that's going to be D alpha 4, D beta 1. That means one of the 5 electrons has the opposite spin as the rest. So it's D alpha 4, D beta 1. Those are going to be quartet terms. And the D alpha 4, so D4 partial term is a D. And then D1 partial term is also a D. So we're going to couple 2 D partial terms to get those quartets. So L equals 2 for a D partial term. So when we couple those, we get everything 4, 3, 2, 1, 0. Everything from 2 plus 2, which is 4, to 2 minus 2, which is 0. And then the letters that go along with those are going to be G, F, D, P, and S. Okay? And so those are going to be the quartet terms we get, but remember in the lower spin set, we have to remove those that are duplicated in the high spin. So we got a sextet S from our high spin configuration. That means this is a duplicate term that we have to get rid of. So that leaves us with the following 5 terms: a sextet S, and then a quartet G, F, D, and P. So those are the 5 that you should have gotten. All right, and then the next one is same system. Which of those represents the ground state term symbol? So remember, we do S first, then L, then J. We didn't really even consider J values here. So first we look for the terms that have the highest spin. Well, there's only one term that has the highest spin multiplicity, which is our sextet S. That has to be the ground state. We don't have to compare L values in this case because there's only one L value for the high spin term. So sextet S is the ground state, and then which J values are allowed. So because this is a half-filled orbital, there's only going to be one J value. But what is that J value? So remember that for J, it's going to be L plus S to L minus S. So for a sextet S term, L equals 0 for an S term, and then S equals 5 halves. There's 5 unpaired electrons. 5 times 1 half is 5 halves. And so L plus S is 5 halves. L minus S is 5 halves also. So there's only one allowed J value, which is J equals 5 halves. All right, so in this case, there's only one J value. That's going to be true anytime there's a half-filled set of orbitals. So this is, again, D5 as we're talking about, half-filled. So it's not that a half-filled subshell has no J values. It's just that it only has one allowed J value. So that's always going to be the ground state anyway. All right, the last question here was just some multiple choice questions about coordination compounds. So the first is we want to predict the one that would have the largest delta O field splitting parameter. And so remember that when we have our spectrochemical series, we have, pi donors on one side. This is small delta O. And then on the other side, we have our pi acceptors, which have large delta O and everything in between. So the one that should have the largest delta O would have should have pi acceptor ligands. Moreover, we notice that all of these are the same metal. Cobalt plus 3 is the oxidation state or charge on the metal. And so there's no difference in the metal here. So all that's going to determine delta O is going to be the type of ligand we have. So this one is going to be pi donor because it's chloride, which has filled pi orbitals. So this one's not going to be correct. And then we have to distinguish between CO and CM. Both of these are pi acceptors. And so which one is the stronger pi acceptor is going to determine which one of these has larger delta. The one with the largest delta O should be the one that's the strongest pi acceptor. So if we compare the pi accepting ligands that are common, we have Cn minus, CO, and NO plus are 3 isoelectronic pi accepting ligands. Their field splitting goes in this order here. Now there's different ways of rationalizing this, but essentially if you think about it, if you have a negative charge on the ligand, it's going to be less likely to accept pi electron density from the metal versus the one that's neutral versus the one that's formally positive charge has the largest propensity to accept electron density from the metal, meaning it's the strongest pi acceptor, strongest back bonding interactions. So between cyanide and CO, CO is a slightly better pi acceptor. Moreover, if we draw the Lewis structure of CO, not that formal charges really mean anything, but if this is bonded to a metal, you're going to have a positive formal charge on the oxygen. So again, that really wants to accept pi electron density from the metal to alleviate that unfavorable positive formal charge on oxygen. And so what we get is CO being a stronger pi acceptor than Cn minus, which does not have that positive formal charge. So that's going to be the strongest pi acceptor, so that's going to be the one that has the biggest delta O. The next one here asks us to select the ligands that can be classified as pi donors. So remember that pi donor ligands typically have, all of their p orbitals are filled in their closed shell configuration. And so NH3 does have one available orbital, but that's going to be its sigma orbital. So this one is sigma only. It's only one lone pair of nitrogen that bonds in a sigma fashion. Cn minus, as we just said, is a pi acceptor. It has a sigma orbital on carbon and then 2 empty pi star. H minus hydride only has an s orbital that's filled, so you can't have any pi bonding involving s orbitals. So this is another sigma only. But then these last three here, OH minus, S2 minus, and I minus, all have multiple lone pairs. So for OH minus, it has 3 lone pairs on oxygen, one of them sigma, 2 of them can be pi interactions that are filled pi orbitals, so they're pi donors. Same with S2 minus, it's completely filled P6 configuration. Same with I minus, completely filled P6. So these are sort of 3 of the classic pi donors. So those 3 should have been the ones that you selected as pi donors. And then finally, this one asks which ones of these would have a triply degenerate set of valence d orbitals. And so that's going to be a situation where, when the d orbitals split in these respective point groups, 3 of them transform together under the same representation. So I did give you the character tables, and we should remember for OH, but if we didn't, we have the character table that the d orbitals split into T2g and EG up here. So T2g is a triply degenerate representation, so 3 of those orbitals, XZ, YZ, and XY, all transform as T2g, so that will be one of them. For the TD compound nickel tetracarbonyl, what we have is, in this case, the d orbitals that we split into E and T2. Which again, we covered that in class as well. So tetrahedral also has triply degenerate representations that include our d orbitals, still XZ, YZ, and XY. So that one is the case as well. The only difference is that in this case, the T2 orbitals go above the E orbitals, but it's still a set of triply degenerate orbitals. And then for a D4H compound here, which is square planar, if we look at the character table for this, we notice that we have Z squared there, S squared minus Y squared there, XY there, and XZ and YZ there. In the D4H point group in general, there are no triply degenerate representations, so it wouldn't be possible for the d orbitals to transform together as a triply degenerate set. And we see that the highest degeneracy for any of the d orbitals is the EG set, which is XZ and YZ. So there are no triply degenerate representations in D4H, so we would not want to select that one. Here there's more complex splitting, A1G, B1G, B2G, and EG. So there's 4 orbital levels, but none of them are triply degenerate. Doubly degenerate is the highest. All right, so that takes us to the end. It already took me almost an hour and 15 minutes to go through this, so this was, a bit of a long exam. I acknowledge that. So I went through some of these kind of quickly to try to talk them through in the most efficient way possible. If there's anything that's still not clear, please don't hesitate to reach out to me. And some of this stuff could come back up on the final, so we want to make sure that we're as clear as we can be on it before then. All right, I'll see you guys in class next time.